Our second speaker for this block is Eduardo Vital from IMPA, Brazil. Oh, is the title is you can see the title. Okay.
All right. Thank you for the invitation for the organizer. Today we'll talk about joint work in progress with Eduardo Esteves and Hernan Santos about the generation of linear series to cover 3 components using quiver representations. Right. Essentially, in 2017, Brian Osserman made the following question to Eduardo Esteves in a private method. Do limits of linear series uncovered with more than 2 components have simple bases? Well, in the end of this talk, we'll see how powerful is the existence of simple bases. Well, and we also give an answer to this question by an example. So we start with a motivation. So let's see, be a connected nodal curve with n+1 components and consider a regularized morphism of C. And by regularized morphism, we mean that pi is a projective flat morphism whose the generic fiber is smooth, and the special fiber is isomorphic to C. All right, and this surface X is regular. So let L eta be a line bundle of degree D on the generic fiber of pi. We know that there exists an extension L of L eta for the whole surface. And for each divisor D equal to the sum of NIXI, we also have an extension LD given by this tensor product. Extension of L eta. In other words, for each divisor D, we have this extension of L eta. So you let Ui and U be the multi-degree of xi and L, right? You set LV as LD, where this V here is the multi-degree of LD. Now, for non-negative integer, DNN, we define Zn plus UD as the points of Zn plus 1, such that the sum of di is equal to d, right? And you observe that Ui is Zn plus 1, 0, and U and V are in Zn plus 1d, right? You observe also that the sum of these U0 from Un are equal to 0, and improper subset of U0 to Un are linearly independent over Q, right? These are some properties of these degrees. And for each effective divisor D, gives us a natural map that is non-zero and restricted to the curve C, which will represent by 5 from V1 to V2, from the sheaf LV1 from L to V2, where this V2, this multi-degree V2 is equal to V1 plus the sum of NIUI, right? Now, if you consider the restriction of LV to the curve, right, the map 5 from V1 to V2 induce another map that will keep the node by 5 from V1 to V2, now maps from the sheaves on the curve, the curve C. Thus, we have a quiver Q depending on U, U0 and UN, whose set of vertices is G, that which is equal to U plus Zn 0 to Zn, which is inside Zn plus 1d. And the set of arrows A can be decomposed as a union of AI, such that an arrow from W1 to W2 is in AI for I from 0 to n if W2 is equal to W1 plus UI. Well, this quiver is called the Zn quiver, right? And more generally, the definition of Zn quiver. Let Q be any quiver and then a natural number. A Zn structure on this quiver is a decomposition of the arrows into n+1 subsets, satisfying the following three properties. One, for each vertex of G and each I from 0 to n, there is a unique arrow in AI leaving this vertex, right? And for a path gamma in Q, we consider gamma I the number of arrows in AI that it contains, right? And if this gamma I is equal to 0 for some I, then you say that gamma is called a admissible path. 2. Now, for two vertex V1 and V2 in G, there is a admissible path gamma and Q connected them, these two vertex. And last, if every two path gamma 1, gamma 2 in Q leaving the same vertex arrive at the same vertex, if and only if this difference here is constant for each I from 0 to n, right? So a quiver with a Zn structure is called a Zn quiver, right? And the first proposition is that for each n, all Zn quiver are isomorphic, right? So it's not that difficult to see that this proposition is true, because when you look at one vertex of a Zn quiver, you can observe that in this vertex, there are precisely n+1 arrow leaving this vertex and precisely n+1 arrow arriving at this vertex. So we observe that locally in each vertex, all Zn queens are the same. So the job is proof that it's globally the same, that they are isomorphic. So now let V eta be a subspace of global section of the line bundle L eta on the generic fiber of the smoothie. And for each extension LV of L eta, there is an extension VV of V eta given by the global section of LV on the surface, such that the restriction of this section to the generic fiber is in V eta. Now, does the map, the last map, phi V1 to V2, in the Z map now that we keep denoting by phi from V1 to V2, right? Now as sections, global sections from VV1 to VV2. And again, we consider restriction to the curve now. Now you consider vector space in a global section of the Chivel V in the curve C. Then this map phi from V1 to V2 in the node map that we keep denoting by phi from V1 to V2, now in vector space, right? Then the maps phi V from V1 to V2, this here, and the vector space form a linked net of vector space now, which is more general. Here we define a linked net of vector space. So let Q be a Zn quiver. A linked net of vector space G, we denote by G, is a quiver representation of this quiver Q with pure dimension satisfy the following three properties. First, if gamma 1 and gamma 2 are two admissible paths connect the same two vertex, then the maps of this representation are equal. If gamma is a non-admissible path, then the map phi gamma is equal to 0. And finally, if gamma 1 and gamma 2 are two admissible paths that leave the same vertex, such that gamma 1i is equal to 0 or gamma 2i is equal to 0 for each I from 0 to n, then the intersection of the kernel phi gamma 1 with phi gamma 2 is equal to 0. These three properties define a linked net of vector space, right? So given two vertices V1 and V2, we write phi gamma as the phi from V1 to V2, where gamma is an admissible path connecting V1 to V2. In other words, given two admissible path connect V1, V2, the map doesn't depend on the path, just from the initial and final vertex. And the path gamma with gamma I smaller or equal to 1 for all I is called simple. And you say that G, the linked net G, is exact if for each vertex V1 and V2 in G connected by a simple path, you have that the image of phi from V1 to V2 is equal to the kernel of the map from V2 to V1. Right? And we say that this linked net G has support on the subset edge of the vertex G. If for each vertex W of the G, there is a V, a vertex V of edge, such that the map from V to W is an isomorphism. And if edge is finite, we say that G has finite support, right? And here, the definition, we call a collection of vectors from V1 to Vm and vectors S, I in VDI for I from 1 to M, such that the image in the subspace V generate the subspace VV for each vertex of Q. This is a set of generators. In the case where M is precisely the dimension of G, the set is called the simple base, right? It's like a vector space. You have vectors, we put them together in the same vertex. If they generate this vector space, we call set of generator. It's minimal, then you call it a simple base. Well, when gamma is a admissible path, simple admissible path, the map phi gamma is determined by its initial vertex V and by the set L, which is the set of I such that gamma I is equal to 1. Thus, we can write a new notation for phi gamma as the map that starts in V along the set L. Then we define that an exactly linked net of vector space over Zn quiver satisfy the intersection property if for each vertex in the collection L0 to Lm of subsets of 0 to n, we have that this equality holds. All right. We know that this equality is true when M is equal to 1. All right. M equal to 1, this is true. So this equal is like a distribution law in the intersection of vector space, subvector space, which you know that in general, it's not true, right? So we have a theorem that an exactly linked net with finite support admits a simple base if and only if it satisfies the intersection property, right? So what this theorem is saying? Well, a linked net admits a simple base is a global property of this representation. And such the intersection property is local. We can see here in the definition, we can verify that in each vertex, this property here, and you can guarantee that this representation admits or not a simple base, which is a global property, right? So we give an idea of the proof of this theorem. And first, we worry about one direction, that if an exactly linked net with finite support admits a simple base, then it satisfies the intersection property. Well, if the linked net admits a simple base, we can describe that kernels of the intersection property with some set theory condition. And this verification is some of the set theory proof is not that difficult. Now the other implication to prove the converse, we proceed by induction the dimension of G, right? So the main tool to prove the converse is this proposition that says if G has finite support, is exact and has finite support, then there is a vertex U of Q such that the image of the maps that arrive at U isn't the whole vector space VU, right? There is this vertex U. And if G satisfies the intersection property, given a vertex U as above, you can pick a vector S in view, but which not can be written as a sum of image. Then the subnet age of G generated by S in the quotient linked net G over H are exactly linked net, satisfying the intersection property, right? So with this proposition, we can apply induction. We obtain a simple base for age. We obtain a simple base for the quotient. And you can verify that the union of a simple base of age with the lift of the average of this quotient is a simple base of G, right? And this proposition is quite hard to prove. And the most difficult part is to prove that this quotient representation is exact and satisfy the intersection property, right? With this, we prove the theorem. Now here we give an example, a very important example, which we use later, that an exactly linked net of vector space over Z2 quiver with support on a triangle quiver Q delta admits a simple base, right? Here the quiver Q delta is this one in red, the vertex V0, V1, and V2. The Z2 quiver is infinite, but here we just draw some vertex, impossible to draw infinite many vertex, right? And you verify the intersection property, you must verify the intersection property just in the vertex of the support. So it's not difficult to verify that V0, V1, and V2 satisfy the intersection property and use the theorem to conclude that this linked net admits a simple base, right? And another example here, which gives a negative answer to the question arised by Brian Osman in 2017. Well, here is the very step following the motivation. We will obtain a linked net, exactly linked net, which arises as a degeneration of a linear series, right? So let's see delta be this curve in the projective plane. And we define the smooth surface X as this Vance set in the product of P2 with A1, right? Thus, when we consider pi, the map pi as the restriction of the projection in the second factor here, we observe that can conclude that pi is a regularized morph of C delta, right? Thus, we consider the sheaf of conics and the following linear series. A pencil of conics restrict the generic fiber of this smooth, right? Here is our L8 on the definition of the motivation, right? And we obtain the following exact linked net of vector space from this degeneration. Here is the moot degree of each line investible sheaf. For example, here at C222 is the moot degree of the sheaf of conics, right? Here again, the Z2 quiver is infinite, but we just draw the effective moot degree. If you observe how moot degree are effective, and which is a verification, we observe that here, this moot degree 222, the intersection property is not true. This right side is 0 and the left side is not. So in this linked net of vector space, the intersection property is not satisfied at this vertex 2, 2, 2, so it does not admit simple base, right? Which gives a negative answer to the question of Bryan-Osman. Here, we define the linked projective space, right? So given a linked net of vector space G over Zn quiver Q, with support on a finite subset H, the linked projective space, which we denote by LPG H, is defined as the points of the product of projective space with U in H, such that the image of SV1 wedge the SV2 is equal to 0 for each arrow from V1 to V2 with V1, V2 in the support edge, right? So we have a theorem about this linked projective space. Actually, this linked projective space is a quiver Grassmannian of one-dimensional subspace of this representation, right? This is just a special case of a quiver Grassmannian. So when this H has some property, a special property, which is not that very specific, we can omit this H, which we'll do here in this theorem, right? So let G be exactly linked net of vector space with finite support over Z2 quiver. Then the linked projective space LPG is Cohen-Macaulay, reduced, connect, and has pure dimension R. Well, essentially, we try to study some property, geometrical property of this scheme LPG. Well, and the next we give an idea of the proof. What step of the proof of this theorem? For each vertex U in the support, you define open LPG U star as the point of LPG such that the image of SU from U to V is non-null for each or all vertex V on the support. It's open. It's not difficult to see that this open is isomorphic to an open set of PDVU. Thus, it's reduced, non-singular and reduced or reducible of dimension R if it's not empty. Because if some of this map here from U to S is 0, then this LPG U star is empty. All right, so we must consider the case when this open is empty. So we define LPGU as the series closure inside LPG of this open, and you use this following two theorem, right? That linked net of dimension 1 with finite support of Z2 quiver generated by a triangle, meaning that for each point of LPG, we can generate this point from 3 vertex of a triangle, form a triangle. And the next element that says that if G is exactly with finite support as over Z2 quiver, then the following two statement holds. This LPGU cover LPG, right? And when you consider this intersection is non-empty, if and only if this vertex is contained in a triangle, right? So it follows that LPG is the union of LPGU, thus it's generically reduced of pure dimension R because each of these components has dimension R and it is reduced. So now it's enough to prove that LPG is Cohen-Macaulay because it will imply that generically reduced and Cohen-Macaulay is reduced. And we'll do it proceeding proving that LPG is locally given by the right number of independent equations inside the product of projective space. So we know the dimension of this product of projective space. We know the dimension of LPG. So we know the expected codimension of LPG inside this product of projective space. Now, we prove it in 2 steps. One, we prove the theorem for a linked net with support in the triangular quiver. Then after that, use this first step to conclude, right? So, assume that C is exactly linked net with finite support on the triangular quiver. So we know by the example that this C admits a simple base, which allows us to write each vector space Vi as the sum Vi0 plus Vi1, where Vi0 is the subspace of Vi generated by the elements of the simple base of V0 and analogs for the others subspace, right? So when you consider the projection Pij from Vi to Vij, you define the open set Dij as the point of Euclid C. C here is the linked net with support on the triangular quiver, and Pij of Si is non-zero. You can verify that you can cover Euclid C with this union of these open sets. And for each of these open sets, we count the number of independent equations among the defined ones of LPC to obtain 2R. All right, so is what we wanted, because we are in the triple product of projective space, which has dimension 3R. We have LPC inside this product of projective space, which has dimension R, and the codimension is 2R. All right, so the results true for a quiver, linked net with support on the triangular quiver. Thus, C here is Cohen-Macaulay. Now, the second step, that using the classification of the points of age of LPG, we can find an open neighborhood UH, which is isomorphic to an open subscheme of LPCH. Right? For a certain exactly linked net CH with finite support on the triangular quiver, right? So we showed that for each point of LPJ, we found an open neighborhood of H, which is Cohen-Macaulay. Thus, we conclude that LPG is Cohen-Macaulay and thus reduced. Right? Now we talk a little about further questions. Right? When the limit curve C is of compact type with 2 components, the corresponding quiver is a Z1 quiver. And Daniel Rocha proved that the multivariate Hilbert polynomial of LPGH is equal to the multivariate Hilbert polynomial of the diagonal scheme side of the projective product of projective space. Yeah. For any exactly linked net, G with finite support on H, all right? But here in a Z1 quiver. And he used that the Hilbert polynomial, the linked projective space is Cohen-Macaulay, using an idea due by Breyer-Osserman. So here is implicit that he used that LPG is Cohen-Macaulay. And the theorem is that when G arises as a flat degeneration, its multivariate Hilbert polynomial is equal to that one of the diagonal. For a G, a linked net over a Z2 quiver. This is the result for a G over Z2 quiver. And this theorem is very useful and powerful because it's the case when G admits a simple base or G arises as a degeneration of a linear series. So this theorem, as a corollary, we can conclude that when G admits a simple base or as a degeneration of a linear series, its Hilbert multivariate Hilbert polynomial of LPG is equal to that the diagonal. All right. And with the collaboration of Oliver Loschard, we could prove more like general result that almost in the same case when G is a linked net over Zn quiver, the same result is true. but it's a study in the very beginning with the help of Oliver Loschide, so doesn't state this result. So this is, thank you, everyone. Stop.
Okay, thanks, Eduardo.
I think I'm on time.
Questions or comments? No comments? Okay, thanks again to Eduardo.